Okay, so now that we've seen the continuity equation and Bernoulli's equation under fluid flow, let's now consider a couple examples and see how this actually works. So, first example we're going to look at is, let's say we have a rain barrel here, which has a cross-sectional area A1, and then some distance, 0.8 meters below that is a spigot, which has a cross-sectional area of A2. Now, for part A, we then want to say, okay, so let's say the spigot is pointing horizontally. We want to know how fast is this rainwater flowing out to the right here. So what is the velocity or the speed of the water as it comes out through the spigots? Part B, we then want to take the spigot and point it upward. So that way it's now coming out with V2 straight upward. And we want to know to what height, Y2, does the water reach? So what height does the rainwater make it to? So let's look at this problem. So here, let's apply Bernoulli's equation. So Bernoulli's equation again says that the pressure at 1 plus 1/2 the density of the velocity 1 squared plus then rho times g times y1 must be equal to the pressure at point 2 plus 1/2 rho times v2 squared plus rho times g times y2. Okay. Now here, let's say this barrel, since it's collecting rainwater, is open to the atmosphere, which means that up here we have atmospheric pressure. The spigot comes through, but also out here it opens up to the air, which means this is also at atmospheric pressure, which means here that the pressure is also at atmospheric pressure, and here the pressure is also at atmospheric pressure. So this means that P1 and P2 are exactly the same. They're both just atmospheric pressure, which means that these two things are going to cancel. Okay. So those two are both at atmospheric pressure. So this means then, and I'm left with the remaining, which each one of these parts actually depends on the density, which means all the densities are going to cancel, so I actually don't care about the density. So I don't care about the density of the rainwater is, which is nice. Now the other thing is, we can choose that this is our y is equal to 0 location, which means that y2 is simply equal to 0, and y1 is going to be equal to h. So finally you can write this as 1/2 v1 squared plus, g times h, or like capital H, not little h, is then equal to v2 squared plus 0, right? So this tells me automatically then that v2 is then simply equal to the square root of 1/2 v1 squared plus then g times h. Great. So this means to determine how fast it's coming out of here, I need to know how fast the water is moving up here at this point. Now this is where the continuity equation comes in. So again, what I said is that Bernoulli's equation almost never goes without the continuity equation. So the continuity equation says that A1 times V1 must be equal to A2 times V2. Now, here I never actually told you what A1 was and V1 or what A2 are, but you know, we can kind of use our imagination on this. So a barrel usually has a nice big large cross-sectional area, right? So I have something like this. So this is my A1. A spigot is going to be something more like that, right? So basically what this says then is that V1, the velocity is at the top, must be equal to A2 divided by A1 times V2. But A2 we know is something small. A1 is something very large. So what happens if I take something small and I divide it by something large? Well, I get something smaller, right? So here, since this is something very small and this is something very large, this is simply going to be approximately equal to 0. So up here we can say is that the rainwater that's up here is barely moving, if not moving at all, and it's rocketing out of this little spigot down here. Mm-hmm. So here we can simply say that this guy is approximately equal to 0, so this is equal to the square root of g times h is equal to v2, so it's the square root of 9.8 times 0.8 is v2, which works out to be, if I remember right, about 4 meters per second. So good. So this is our velocity by the time it comes out through the bottom. Yes, 4 meters per second. Good, so that's part A. Now part B, we're going to basically do the same thing. So let me erase all of this. So now for part B. Now again, I'm going to leave it much the same way. So basically what's going to happen here is that, again, P1 is going to be equal to P2 for the same reasons. The spigot is still open to the air. The upper parts is still open to the air, so those are both still atmospheric pressure, so they're both still going to cancel. So all the rows are going to cancel. So in this case, we're going to get V1 squared plus then GY1 is then equal to V2 squared plus GY2. Now, before we go any further, oh, sorry, I forgot my 1/2 here. There we go. So, again, let's have a little comments. You guys can write something in the comments. What do you think is going to happen? So, is the water which is going to come off, is it going to reach the same height at which it started, i.e. is it going to go back to H, or is it going to be something less than that? So what do you think? So what does conservation of energy tell us it should be? So again, pause the video now, write a little something into the comment section saying how high do you think it's going to go? Is it going to go back to H, or is it going to go to something lower than that? Good. All done? Great. Let's keep going. Now again, we know from here that V1 is basically equal to 0, right? So here we know that this is going to be what? G times H is then equal to 1/2 of V2 squared plus G times Y2. Now from here, there are two ways to do this problem. Either we can take this all the way down to here and then call Y2 equal to 0, so that we have V2. But then once we have V2, we have to apply conservation of energy again, because now we know the water has V2 and we have to figure out the maximum height at which it goes. Or we can simply say, well, from here, we know it's coming out down here with V2, but instead of calling down here V2, we can actually call this point our V2, in which case, to reach its maximum height, the water has to momentarily stop. Right? It's going to move all the way up to the top, turn around, and then come back down. So if we do that, which is the version I'm going to do, I'm going to say, well, let's take T2, or point 2 actually up here, which means V2 is actually going to be equal to 0, which means then that G times H must be equal to G times Y2, which means H is equal to Y2. So meaning that the water that started here is going to come down, go through the 2, and then come all the way back up to the same amount of height of H. Now, is that what you said? Don't lie. So, now, this makes sense because the velocity here and the velocity here are exactly the same. So since the velocity and velocity are the same, that means they have zero kinetic energy, so all the potential energy turned into all the potential energy, so it has to reach exactly the same height. Now, this wouldn't be true anymore if I say gave it a velocity here. So if it did have an initial velocity here, which was non-zero, by the time it comes out through this side, it's actually going to reach a higher location, because now I have gravitational potential and kinetic energy. Those two have to now go into only potential energy, which means it has to actually reach a greater height. So in this case, if it started off with a non-zero velocity here, i.e. this term didn't go away, in this case then Y2 would have to be then the sum of these two energies together. So, but in this case, since it starts off with an initial velocity of 0, ends with an initial velocity, or a final velocity of 0, those two heights have to be exactly the same. So let's do one more. And then we can be done with fluid flow and Bernoulli's equation for a while. Now, one other thing I'll point out about Bernoulli's equation, which I didn't point out during the actual video lecture portion of it, when it comes to the exam, so this 5th exam, typically Bernoulli's equation is not going to be in a long problem, it's only going to be in a short problem. So this would only show up in a short answer quick calculation type problem. So great. So the next one says that we have some container. So here's my container. So here's my container, and this thing is full to some height h. So this is the height of the container h, where the height of the container is equal to 40 centimeters. And then we're going to put a hole some distance down. So this is the distance of the hole. So let's call this height little h, where little h is actually 10 centimeters in this case. And then we're going to have water firing out in this direction. Now, what I want to know is, since the water's coming out over here, it's then going to undergo parabolic motion, so it's going to hit the ground some distance then x away from the base of this container. So here, for part A, what I want to know is, what is that distance of x? Part B, we then want to know, okay, so let's say I block this hole, and then I put another hole some distance down here. So this is my other hole. So let's call this a distance, I don't know, h prime. So what I want to know is, what height, h prime, do I have to put this guy at so that the water which is coming out of here ends up going under parabolic motion to the same exact distance as before. So I want this x to be exactly the same. So I want to know, what distance of h prime do I have to cut this hole while blocking this hole to make it undergo parabolic motion to be exactly the same. And then finally, what I want to know is, I don't know, let's put it somewhere about here. If I block this hole and I block this hole, so what is now this distance, h max, what is this guy equal to? So that this water is going to go under parabolic motion to then get the maximum distance of x. So I'm looking for then x. I want to extremize x. So what is the maximum distance I can get in this case? Okay, so where do I have to put this hole to get the maximum distance? So let's look at part A first. Now again, let's say this has a large cross-sectional area, this has a small cross-sectional area. So again, using the continuity equation, what has to be true then is that this velocity up here has to be equal to 0. Again, same exact reasons as for the rain barrel. Again, if this has a large cross-sectional area, this has a small cross-sectional area, then this velocity up here has to basically be 0. So by Bernoulli's equation, we can then determine how fast the water is coming out of here. So let's call that V2. So this is our point 2. And let's take that this is our y is equal to 0 location. And what else do we need here? And again, let's say this is open so that this is at atmospheric pressure. And this is also at atmospheric pressure. So again, Bernoulli's equation says that the atmospheric pressure plus 1/2 times rho times v1 squared, which we already established is equal to 0, plus g times rho times h must then be equal to the atmospheric pressure, plus 1/2 rho times v2 squared plus 0, because again we're calling that our y is equal to 0 location. So again, all this means is that this term has to cancel with this term. So this tells me, again, the rows are going to cancel. So I get that v2 must again be equal to the square root of g times h. So that's v2. So now we know that the water is coming out of here with the square root of g times h. Now, what else do we know? So now we know that it's going to go under parabolic motion from here. So we know the distance that this is going to fall from here is going to be the same thing as capital H minus little h. So this is capital H minus little h of distance. We also know that water is coming out only horizontally. So in the y direction, there is no portion of velocity in that direction. So here we can say that y then is equal to the initial height, which is going to be our h minus h, plus the initial velocity, which is 0, minus 1/2 gt squared. Right? So again, here I'm saying that this is my base, this is my y, points in this direction, x is going to point in this direction. We know gravity points downward, so that's where the minus 1/2 g comes from. So we're just going all the way back to chapter 4. Right? Now again, we know this thing hits the ground when y is equal to 0, so we get 0 then is equal to h minus h, minus 1/2 gt squared, which means the time it takes is equal to twice of h minus h divided by g squared rooted. Now, to find the distance x at which it goes, we need to look at the x direction. So here we have x then is equal to the initial velocity, which is simply v2, times the amount of time, where that amount of time is this amount of time. Remember, the amount of time it takes to fall this distance is the same amount of time it takes for this to go in this direction. So this is going to be v2, which is the square root of g times h, times the time, which is the square root of 2h minus h, all divided by g. So this g is going to cancel with this g, so it's going to be the same thing then as the square root of 2 times h minus h. So, plug in our numbers, we find in this case then is that this ends up going 35 centimeters to the right. Good. So x is equal to that. Good. So good. So that's part A. So part A, we're just using, again, continuity equation, using the fact that, again, small cross-section area, large cross-sectional area, so this has to be zero velocity, followed by Bernoulli's equation, and then from there, projectile motion that we've done 1,000 times way back when. Great. So now what? So now part B. So part B now says, okay, we're going to block this hole, and what we want to do is find a new hole, H prime, which then is simply to get the distance x here to be exactly the same. So we want it to go exactly the same amount of distance. Now the way we're going to do this is we're simply going to start off with this solution here. Okay. So since we know x is equal to that, we know x is 35 centimeters, so we're going to use that. Now we're simply going to take that guy and square it. Okay? Because ultimately what we want to do is find out what is h here. So let's do that. So we want to take that expression and then simply square it and then solve for h. And what we'll find, kind of a prelude, is what? That we end up with two expressions. So let me rewrite this here. So this is 2h times h minus h. Good, so I can get rid of this one as well. Let's do that. Great. So, okay, from here, we're going to treat little h as an unknown variable, using that x is known, capital H is known. So let's square both sides. So from here I get an x squared that is equal to 2h times h minus h squared times 2, right? So this is the same thing then as what? X squared is equal to 2h minus 2h squared. Now, if I rearrange this, I get 2h squared minus 2hh plus x squared is then equal to 0. Which basically means that what? I now have two solutions for this guy. Right? So I now have two solutions since this is a quadratic expression and I'm trying to solve for what h is. So let's then use the quadratic formula. So this says that h then is equal to minus b, so minus b in this case is going to become 2 times capital H, plus or minus the square root of b squared, so it's going to be 4 times capital H squared, minus 4 times a in this case is simply 2, times c, where c is the same thing as x squared, all divided by 2a, which is then simply 4. Okay. Good. So from here, I can factor out a 4, so that's then going to give me a, 2. So this 2 is going to cancel with this 2, which cancels with one of those 2s. So it's going to be the same thing then as 1/2 of h plus or minus the square root of h squared minus 2 times x squared. For AC, yeah. Oh, sorry. This should have been a 4. So I had a 2 in each one of those expressions. So it was actually a 4. Sorry. So it should be 4, 4, 4. Good. So it's actually 4, 4. So this is a 4. So this should be a 4 squared. And this is a 4, which is a 4 squared. Sorry about that. So it becomes a 4. So actually all of that cancels. Sorry. So I actually end up with that. Yeah, sorry about that. Good. So this should actually be that guy. Okay. Yeah, sorry about that. Good. So from here we actually end up with then two different expressions. So from here we find that the one which dealt with the negative sign then is the shorter of the two. And then the positive one then is the, let's see here. Yeah. So from here, if I solve this, what I find in this case then is I have two solutions. The one is 10 centimeters, the other is 30 centimeters. So the 10 centimeters one was the one that we originally started with. So that says that h prime then is simply equal to 30 centimeters. So if I take this guy and then take him to here, then for 30 centimeters below the surface, that is the other location that will give me exactly the same distance. Great. So that's part B. Part C then is now what we want to do is we want to take this guy and then what? Extremize him to find the greatest amount of distance that this thing can go. Okay. So, again, let's start off with him. Let's take an x squared. So we have x squared then is equal to f times h minus h. So that's going to be our function. So this is the same thing then as what? 4 times h minus 4 times h squared. Okay. So we're going to start off with him. Let's call this guy simply f. So what I want to do is extremize x here in terms, or x squared, or f in terms of h. So basically what I want to do is I want to take the derivative of this with respect to h. To maximize this, I have to then set this guy equal to 0, and then that's going to tell me the depth at which I have to cut it to then extremize the amount of distance at which it has to go. So let's do that. So if I take the derivative of this, it's going to be the same thing as 4 times capital H minus 8 times little h. Since that's equal to 0, let's divide everything by 4. So I get 0 then is equal to h minus 2 times h, which means little h then. So the maximum to extremize then is going to be equal to a height divided by 2, which in this case then is simply equal to 20 centimeters. So this means then that the location at which I want to cut this below the surface is exactly halfway through the surface, and that's going to maximize the amount of distance at which this thing can travel. So this will maximize then the projectile motion, or how far the water is going to reach from the base of this particular container. So good. So these are examples of, again, continuity equation and Bernoulli's equation. Again, as I mentioned a little bit ago, one thing that's usually going to be true on this upcoming exam is this will not constitute a long problem. It will only be part of a short problem. So meaning it will be one of the short answer, quick calculation problems. Because ultimately there's not too much we can actually ask during one of these problems. But again, this is Bernoulli's equation and continuity equation.